Welcome to solverfy.
So this problem has empirical formulas that we need to find. Remember, to find empirical formulas, we need to convert to moles of each element and then divide by the lowest number of moles. In the first problem, we have toluene, which has some number of carbons and hydrogens. We don't know how many. They're telling us it's undergoing a combustion reaction to produce CO2 and water. Now, the reaction itself doesn't really matter, but I often like to write these out because it gives me a way to organize my thoughts as I go through these problems. They gave us two masses. The first is 5.86 times 10 to the minus third grams. That's for the CO2. The water is 1.37 times 10 to the minus 3 grams. We need to convert these both into moles, and not just moles, but moles of the carbon and moles of hydrogen, because those are the two elements that are in our compound. The nice thing about this compound, we only have carbons and hydrogens, so every single carbon in CO2 came from the toluene. Every single hydrogen in the water came from the toluene. So when we convert these, we're looking strictly at how much we're dealing with in terms of subscripts for carbon and hydrogen. All right, let's get this math done. We'll start with the CO2. We have 5.86 times 10 to the minus 3 grams. I need to get it into moles, so I'm going to divide by the molar mass. And then I'm looking just at carbon. So here in 1 mole of CO2, I have 1 mole of carbon. And that is going to give me 1.33 times 10 to the minus 4 moles of carbon. For the water, we're going to do 1.37 times 10 to the minus 3 grams. We're getting this into moles. So we're dividing by 18.02, which is the molar mass of water. And then in every 1 mole of H2O, I have 2 moles of hydrogen because of that subscript of a 2. This gives me 1.52 times 10 to the minus 4, and that was our moles of hydrogen. Now that we have these two values, we can look at the one that is smaller. So 1.33 times 10 to the minus 4 is smaller than 1.52. We're going to divide both of them by this value. Obviously, when I divide carbon, I'm going to get 1 because that was the one that was smaller. When I do that with the hydrogen, I get 1.14. Now, normally on these, if you're close to a whole number, you round it, and you're looking for a value that you can multiply both of them by in order to get a whole number ratio. This may not jump out at you right away, that you can actually multiply the 1.14 by 7 in order to get a whole number. So we also have to multiply the top value of 1 times 7. So for carbon, we get 7. For hydrogen, when we do this, we're going to get 8. These two values give me my mole ratio. They also become my subscripts. So this is C7H8. So that one wasn't really too bad until we hit the end. The second problem is a little bit more complicated. In the second problem, they're giving us a compound that contains carbon, hydrogen, and oxygen. And that's burning in oxygen to give us CO2 and water. Well, in the last problem, it was nice because all of the carbon and all of the hydrogen came from the compound in terms of the products, but now we have oxygen added into this compound. So we're not really sure in our products where these oxygens came from. However, they do give us masses for the CHO compound of 0.1005 grams. They give us the mass of CO2 of 0.2829, and they give us water at 0.1159. Okay, and these are all grams. What's nice is I can use the law of conservation of mass that says the masses of our reactants has to equal the mass of my products. So we can just do this and change this into an algebraic formula. 0.1005 grams of our unknown compound plus X has to equal the mass of carbon dioxide plus the mass of water. When you solve this, you should get your X, or your mass of oxygen, to be 0.2983. Now that is the grams of O2. I'm going to leave that alone for now, and we'll come back to it. I'm going to tackle the CO2 first. 0.2829 grams of CO2. We're going to get that into moles. And then, just like before, we have one carbon for every one CO2. So this gives me 6.428 times 10 to the minus 3 moles of carbon. I'm going to actually do the same thing to get the moles of oxygen. So we're going to copy that. I'm not going to rewrite it, but we're using the beginning portion of it. And then instead of 1 mole of carbon, we're using moles of oxygen down here. So for each CO2 that I have 2 moles of oxygen. This gives me 0.01286 moles of oxygen in CO2. And I'm going to write that in just so I know where that one came from. We also have to use the water. We need to find moles of both oxygen and hydrogen from there. I'm going to start with oxygen. So 0.1159 grams of water. Get it into moles. So we're dividing by molar mass. Then we're doing 1 mole of O2 for every 1 mole of water. This gives me 6.43 times 10 to the minus 3rd moles of oxygen in water. Now, I have moles of oxygen here, I have moles of oxygen there, and way back up here, I have the mass of the oxygen that we started with in terms of what the unknown compound reacted with. I need to put this into moles. So we're going to do that next. Change it to red. 0.2983 grams of oxygen. I'm going to just divide it by 18.02 to get it into moles. This gives me why did I do 18.02? I don't even know. It's oxygen, not water. Hang on. Losing it today. So this is divided by 32 grams per mole. And then in every O2, there are 2 moles of oxygen for every 1 mole of O2. Okay. This gives me 0.01864 moles of oxygen. Now, this number in red is the amount of oxygen that came from O2. The numbers in blue here and green here are the values on my product side. So if I add these two values in red, in blue and green together, I can subtract out the mass of oxygen in red, and it will tell me how much oxygen is in that CHO compound. So that's what I'm going to do next. We'll switch it to black. We have 0.01286 plus 6.43 times 10 to the minus third. This gives us 0.01929 moles of oxygen on the product side. I am going to take that and subtract out the 0.01864 moles of oxygen from the reactant side that we know about from O2. This is going to give me 6.500 times 10 to the minus fourth moles of oxygen. This is how much oxygen came from the CHO compound. So now I have that. I also, at the moment, have the value for carbon. There is one that we still need to calculate, and that's hydrogen. And then we can divide those numbers that I put in the boxes by the smallest value. So I'm going to try and squeeze hydrogen so you can see them all on one page. I'll go back to blue for this one. So we're really copying what we did up at the top, but it was up in this green section. 0.1159 grams of water. I'm going to divide it by 18.02 to get it into moles. And now in this part, I'm changing this into moles of hydrogen. So 2 moles of hydrogen in every 1 mole of water gives me 0.01286 moles of hydrogen. So now that I have these 3 values, I can find the smallest one and divide by it. I'm going to divide all of these by the smallest. That smallest value is the one for oxygen. So I'm going to scroll down and kind of start this fresh. In terms of carbon, we had 6.428 times 10 to the minus third. We're dividing that by the smallest value from the top, which is 6.5 times 10 to the minus fourth. This gives me 9.88. For oxygen, we had 6.5 times 10 to the minus fourth. I'm dividing it by itself. So this should give me 1. If you don't get 1, you did something wrong. For hydrogen, we have 0.01286. Again, dividing by 6.5 times 10 to the minus 4. And this gives me 19.78. Now, in the last one, I looked at it and I could tell that I needed to multiply by something. This one, when you first look at it, you might think you do need to multiply. but you can try. You can sit there and try and figure out a number that's going to get you whole numbers for all of these. But I'm going to tell you, you're wasting your time. You're not going to find one. So what you're going to do here is you're going to just round. This is going to round to 10. This one's going to round to 20. And we are going to get C10H20O as our empirical formula.